Every HTTPS connection starts with three random numbers you've never seen. Your browser and the server each flip 256 coins and somehow end up with the same encryption key. When you connect to any HTTPS site, your machine kicks off a TLS handshake. Here's what that looks like under the hood. TLS 1.2 shipped in 2008. It's still running a huge chunk of the internet's secure traffic, and nearly 30% of those connections have a fatal flaw. If you're using RSA key exchange, an attacker who records your encrypted traffic today can decrypt every byte of it the moment they steal the server's private key. No quantum computer required, just patience and a hard drive. Every API call, every login token, every password reset email sits there waiting to be read. So let's crack open the handshake and see where those three randoms come from. The TLS 1.2 handshake is a two-round trip dance. Client says hello. Server says hello back, proves its identity, and asks for a key. Client sends the key, both sides flip the switch, and application data flows. The client hello carries the protocol version, a 32-byte random nonce, and a list of cipher suites the browser supports. Random number 1. The spec originally said the first 4 bytes should be seconds since 1970, but that's a fingerprinting risk and enables clock skew attacks, so modern browsers just fill all 32 bytes with random data instead. The timestamp is now a lie by design. The server picks one cipher suite from the client's list, generates its own 32-byte random, and sends it back in the server hello. Random number 2. Next, the server sends its certificate, which chains up to a trusted root authority. The client verifies the signature, checks the domain name matches, and extracts the server's public key from the certificate. Now comes the third random, the premaster secret. The client generates a fresh 48-byte random value. This is the secret that never goes on the wire in plaintext. In TLS 1.2 with RSA key exchange, the freshness of the master secret depends crucially on the freshness of the client's premaster secret. All three random values feed into the key derivation function to produce the final shared secret. How the client delivers that premaster secret determines whether this connection has forward secrecy. RSA key exchange encrypts it with the server's public key and ships it across the network. Diffie-Hellman never sends it at all. Both sides compute matching values from ephemeral keys that are discarded after the session. If you're using RSA, the server's long-lived private key decrypts the premaster secret. Steal that key once, and you can decrypt every recorded session that ever used it. Past, present, and future. Every API call, every login, every password reset email. This is the harvest now decrypt later threat model, and it requires no quantum computer at all. Here's what a real client key exchange looks like on the wire when using RSA. The client encrypts the 48-byte premaster secret with the server's RSA public key. The ciphertext is 256 bytes for a 2048-bit key. Time to turn randomness into keys. TLS 1.2 runs all three randoms through a pseudo-random function. The formula is an RFC 5246. PRF of premaster secret, the literal string master secret, and the concatenation of client random plus server random. The output is a 48-byte master secret. The PRF is not a single hash. It's HMAC 256 run iteratively until you've generated enough bytes. You seed it with the premaster secret and a label, then keep hashing until the output reaches 48 bytes. Each iteration feeds the previous output back into the hash. From that one master secret, the PRF expands 6 separate keys: client write key, server write key, client MACI key, server MACI key, and the 2 initialization vectors. Each side encrypts with its own key and verifies with the other's MACI. The key expansion formula runs the same PRF, but now the master secret is the input, and the label is key expansion. The seed is server random concatenated with client random in reverse order from the master secret computation. The output is sliced into chunks for each key and IV. Both sides send change cipher spec to activate the new keys, then immediately send an encrypted finished message. The finished message contains a hash of every handshake message exchanged so far, proving both sides computed the same master secret and derived identical keys. The verified data is itself a PRF output. It takes the master secret, the label finished, and a hash of all handshake messages exchanged so far. If the server can decrypt and verify this message, it proves the client computed the same master secret from the same handshake. Both sides now trust the keys are synchronized. Handshake complete. Application data flows encrypted with AES or ChaCha. authenticated with the MAC keys. Every byte is safe from eavesdropping, unless you pick the wrong cipher suite. Now, the honest part. In 2014, researchers published the triple handshake attack. An active man-in-the-middle attacker performs 3 successive handshakes between an honest client and server, and succeeds in synchronizing the master secrets across connections. The attacker can then impersonate either party. The flaw? The master secret is not cryptographically bound to the client and server identities. Session resumption only checks that you share the same master secret, not that you're talking to the same party. An attacker who can manipulate handshakes can impersonate the client. Session resumption is supposed to be a performance optimization. 2 parties who already established a master secret can resume with new encryption keys using an abbreviated handshake. No public key cryptography, no certificates, just a shared secret. But it doesn't re-authenticate the identities. If an attacker can synchronize master secrets across 2 separate connections, they can hijack the session. The fix is RFC 7627, the Extended Master Secret extension. It redefines the master secret to include a hash of all handshake messages. Now the secret is bound to the actual conversation, not just the randoms. The Extended Master Secret extension is now mandatory in any secure TLS 1.2 configuration. Without it, the triple handshake attack can be applied, which eventually leads to the creation of 2 TLS sessions with the same master secret. The attacker wins. TLS 1.2 shipped in 2008. The triple handshake was disclosed in 2014. Extended Master Secret became RFC 7627 the same year. TLS 1.3 arrived in 2018 and stripped out every vulnerable cipher suite. RSA key transport, CBC mode, RC4, SHA1, static Diffie-Hellman, all gone. TLS 1.3 makes forward secrecy mandatory. It only supports ephemeral Diffie-Hellman key exchange. The premaster secret is never encrypted and sent. Both sides compute it independently from ephemeral keys. Even if you steal the server's long-term private key, you can't decrypt past sessions because the ephemeral keys were already discarded. Quick recap. 3 random values: client random, server random, and premaster secret. Feed the PRF to produce a master secret. That master expands into 6 keys for bidirectional encryption and authentication, and the cipher suite you pick determines whether a stolen private key can decrypt your entire history. As of this year, 29% of live TLS 1.2 deployments still use RSA key exchange. Every one of those sessions can be decrypted retroactively if the private key leaks. No quantum computer, no zero-day exploit. Just patience and a stolen key. 3 randoms walk into a bar. The bartender says, "We only serve cipher suites with forward secrecy." 2 of them leave.